Next is their atomic radius. Because noble gases are present on extreme right of the periodic table, so as we move from left to right, their atomic radius must decrease. But it is not so, because they are present in monoatomic form, as they have stable configuration. That's why they are present in monoatomic form. So I'll try to show you with this कि as we when we move from left to right, their atomic radius will decrease. But it's not in the case of noble gases, because in case of noble gases like neon, it's showing van der Waal radius, means between two atoms. So that line is atomic radius, and this one is H2 molecule. In H2 molecule there is overlapping of these two hydrogen atom, and it will give us covalent radius. But in case of noble gases, they will show van der Waal radius. So that's why their radius is increases as compared to covalent radius in case of all other elements. So atomic radius of noble gases, they are largest in their respective periods because they show van der Waal radius, and on moving down the group, atomic radius increases. Next is ionization energy. They have highest ionization energy because of their stable configuration, and down the group as size increases, ionization energy decreases from helium to radon. Next is electron gain enthalpy, because they have fully filled configuration. So electron gain enthalpy is positive. Why it's positive? Because it's already have fully filled configuration. They don't require any electron. But if we forcefully add electron, then we have to pay it. Means we have to give them energy, because they themselves don't want to take any electron. But if we'll add additional electron to it, so we have to supply energy to them. That's why they have positive electron gain enthalpy, and on down the group it becomes less positive, because tendency to accept additional electron decreases, and that's why electron gain enthalpy also decreases, means becomes less positive. Next we'll move to melting and boiling point, because they exist in monoatomic form, so that's why they have low melting and boiling point. And down the group, melting and boiling point increases due to increase in van der Waal forces of attraction. Next is liquefaction, because they exist in monoatomic form, so they have interatomic forces are weak forces, therefore they can easily liquefy at very low temperatures. So this is all about physical properties. Now we'll move to chemical properties of noble gases. Noble gases, they are chemically inert because of these reasons. First of all is they have completely filled configuration, that is NH2NP6. Second is they have highest ionization energy, and third is positive electron gain enthalpy. Therefore noble gases can neither lose or nor tendency to gain electron, and hence they do not form chemical compounds. And before 1962 it was thought that they cannot form any compound, but in 1962 Neil Bartlett, that is N. Bartlett, observed that platinum hexafluoride, which is PTF6, it's a powerful oxidizing agent. It can react with dioxygen to yield an ionic solid, which is dioxygenyl hexafluoroplatinate 5. Its formula is O2 positive PTF6 negative. And when this platinum hexafluoride combined with oxygen, both are in gaseous state, it will give us dioxygenyl hexafluoro, because 6 fluorine atoms are there, platinate 5. Why this 5 is its oxidation state, that will do detail in chapter coordination chemistry. There you know the meaning of this square bracket also, as well as how we'll write these names, that will clear to you in that chapter. So in this reaction, oxygen has been oxidized to O2 positive by platinum hexafluoride. And why now? Because its first ionization energy of xenon, that is 1170 kilojoule per mole, is very close to that of oxygen. So N. Bartlett thought that if it can react with oxygen, so it's having energy, ionization energy similar to xenon. So why xenon can't react with platinum hexafluoride? So N. Bartlett tried to do a reaction between xenon and platinum hexafluoride at room temperature, and he was surprised to see a rapid reaction occurred, and a red solid with the formula, that is Xe positive PtF6 negative, was obtained, that its name is xenon hexafluoroplatinate 5. So after this discovery, several other compounds of xenon were synthesized. For example, xenon difluoride, xenon tetrafluoride, xenon hexafluoride, and xenon oxychloride. I have given you some compounds, stable compounds of xenon in tabular form with oxidation state of xenon. If it's having +2 oxidation state, it will form you xenon difluoride. If oxidation state is 4, then it will give us xenon tetrafluoride. One more chemical compound, that is xenon oxydifluoride, and when +6 oxidation state, then it will give us xenon hexafluoride. XeOF4 is xenon oxytetrafluoride, xenon dioxydifluoride, and xenon trioxide. When +8 oxidation state, then it will give us xenon tetraoxide, and this is XeO3F2, xenon trioxydifluoride, and so on. Now this I have tried to show you in tabular form, that is hybridization and shapes of xenon compounds. This all are the molecules along with their hybridization and along with their shape. So this is all about its compounds. Now we have to do shapes of its compounds, like xenon reacts directly with fluorine under appropriate conditions to form 3 binary fluorides. First one is xenon difluoride. Its method of preparation is xenon and fluorine in the ratio. This ratio is necessary to, it's mandatory to learn here, along with its temperature. So when 2:1 ratio of xenon and fluorine will combine with one another, it will give us xenon difluoride. And its shape is, as earlier we have done by hybridization formula, because it's having 8 valence electron and fluorine is monovalent atom, so it is 1/2. 8 plus 2, it comes out to be 5. Now 5 out of this 5, how many bond pairs it will form? Only 2, because 2 fluorine atoms are there, so it will form 2 bond pair and 3 lone pair. So this one is its geometry, 3 lone pair and 2 bond pair, and its geometry is linear in shape. And upon hydrolysis, this hydrolysis reactions are very important from examination point of view. Xenon difluoride on hydrolysis means its reaction with water, it will gives how many hydrogens are here? 4. So it means 4 hydrogen will combine with 4 fluorine to give us 4HF, and rest will get xenon with oxygen. Second one is xenon tetrafluoride. When xenon and fluorine in the ratio 1:5 will combine in the presence of nickel as catalyst at 873 Kelvin. Here temperature is 673, but here is 873. The pressure 6 to 7 bar, then will get xenon tetrafluoride. and its geometry is xenon tetrafluoride having 6 sigma bonds. Out of this, how many will form bond pair? 4. So 4 bond pair and 2 lone pair. So this is its geometry, which is square planar geometry. These shapes already we have done in +1 4th chapter chemical bonding. So upon hydrolysis, this xenon tetrafluoride will give us xenon with how many HF? Here see 8 hydrogens are there, will combine with 8 fluorine to give us 8 HF, and rest will get oxygen with xenon trifluoroxide. And upon partial hydrolysis, it will give us xenon oxy difluoride with HF. So these two reactions can come. If it's given you have to write partial hydrolysis, then you will write this reaction, and if on complete hydrolysis, then you will write this reaction. If nothing is mentioned upon hydrolysis only, what happens when xenon tetrafluoride reacts with water? So it's up to you. You can learn, you can write any of these two reactions. Next is xenon hexafluoride. Xenon and fluorine will combine in the ratio 1:20 at 60 to 70 bar and 573 Kelvin. So it will give us 7 sigma bond. Out of this, 6 will form bond pair and 1 lone pair. So these 6 are bond pairs with 1 lone pair, and this geometry is distorted octahedral, and then upon hydrolysis it will give us xenon oxy trioxide and 6 hydrogen fluoride. Now this xenon oxyfluorides means partial hydrolysis will give us these oxychlorides. And this one is geometry of xenon oxydichloride. It's having 5 sigma bond. Hybridization is sp3d with 3 bond pair, because its formula is XeOF2. So 3 are the bond pairs with the 2 lone pairs. So it will give us T-shape geometry. Next is xenon oxytetrafluoride. 6 sigma bonds. sp3d2 hybridization 4 and 1 5 bond pair with 1 lone pair. So it will give us square pyramidal geometry. Now next is very simple. Please go through your NCERT book. That here I have given you uses of helium. It's up to you. You can read from this notes, or either you can go through from your NCERT book. With this we have completed group 18. Thank you.